Welcome to Mr. Retrowolf. In this first episode, we want to do 4 things. First, we'll look at some FPGA boards I have in my collection with pros and cons. Second, I'm going to explain the project we'll do over the next episodes, creating a Namco arcade game from 1980 as a new core on the MiSTer platform. Third, we'll take a look at some resources to help us during the project. And finally, we're going to get an LED blinking on the MiSTer platform using HDL. A nice start to our journey in FPGA. I hope you join me on the way. The learning curve with FPGA development is pretty tough. Each time I'd buy a board thinking it would make life easier, but really you just have to slog through the learning curve to get where you want to go. The boards that I've bought are the MiMus V2 by Namato Labs with a Xilinx Spartan 6, ZR Tech board with an Altera Cyclone 4 chip, MiSTer FPGA by Tim Harbaum, the predecessor to the MiSTer, the D10 Nano by Terasic, the development board for the MiSTer, and the Go board by Nandland's Russell Merrick. The MiMus V2 board from Namato Labs uses the Xilinx Spartan series of chips and uses the Vivato design suite. It's a parallel world to the Altera suite, and they both have different development environments and tools. The Spectrum Next uses the Xilinx Spartan FPGA. The FPGA code you develop is relatively standalone from the FPGA chip you're developing for, but there are some hardware-specific features such as how to deal with memory. I originally bought this board in 2016 as I'd seen someone had done a straight port of Pac-Man onto this device. It's a nice board that has the Spartan FPGA, a VGA port, mini jack for sound, the SD card reader, 3 7-segment LED displays, a small bank of LEDs, some push switches and some dip switches, as well as plenty of interfaces for additional modules. Overall, pretty good for starting out. The ZR Tech WX-EDA board is a generic Chinese manufactured board with an Altera Cyclone 4 FPGA with some DDR SRAM. For in-out, again it's got a VGA port, a small bank of 7-segment displays, together with a beeper speaker, some push buttons and an infrared sensor. It doesn't have a dip switch bank, but its biggest plus point is the PS2 interface plug to be able to plug in an old style keyboard or mouse. This allowed me to get old computer cores going, such as the Apple I or the UK 101. Overall, the board's a bit quirky since there really is no documentation in English, but I've definitely managed to learn a lot using it. One of the main issues with using MiSTer or MiSTer is that there's a lot of additional functionality above the FPGA, and with that comes the requirement to manage it and understand it. By using a simpler FPGA board at the start, you can really get to just worry about the simple FPGA core you're trying to develop without needing to think about the rest. The Go board was developed originally as a Kickstarter by Russell Merrick, and it's used as a teaching aid on his website Nandland. We'll have a little closer look at Nandland in the next section, but just looking at the board itself, it's based on a Lattice ICE 40 FPGA. It's a different development again, and with its own set of development tools. The reason why Russell chose ICE was since the development environment is far simpler than say the Altera suite, which for novices has too much functionality, is really confusing for beginners. If you're starting from zero, it's a good option. The board itself has 4 push buttons, a VGA port, a 2 7-segment display and 1 expansion slot. The downside to the board is that the ICE40 is extremely limited on logic cells for your design, and so you won't be able to implement a CPU in there, let alone any on-chip memory, for simple computers or arcade systems. MiSTer FPGA by Tim Harbaum. The MiSTer was designed to be an Atari ST or Amiga, so taking Minimig, another Amiga-based system, and the ST, making it a MiSTer. It's got an Altera Cyclone 3 EP3C25 FPGA that's relatively large compared to the previous boards, so is only at about 60% capacity when running as an Amiga. This board has an ARM-based I/O controller and SRAM. In terms of in-out connections, it has an SD card slot for your cores, 3 function LEDs, and buttons with the same functionality as the MiSTer. It has 2 9-pin controller ports for all those old-style joysticks. It's got 2 MIDI ports to truly be like the Atari ST back in the day. It has a VGA output, no HDMI on this board, stereo audio output jack, an on-off switch, and 4 USB ports for a multitude of modern-day controllers and keyboards. There's a toggle dip switch for allowing core development and programming by the JTAG interface rather than the SD card slot. The D10 Nano by Terasic, board designer and manufacturing partner for Intel. This versatile system-on-chip board with integrated ARM processor and Altera Cyclone 5 FPGA forms the backbone of the MiSTer project that we know and love. Unlike the previous boards that needed a separate USB blaster to transfer the FPGA files from the PC to the board, the D10 Nano has this integrated and also doubles as the debugging interface when using software such as SignalTap 2 that we'll see later in the video. For simple development, we've got some push switches, toggle switches, and LEDs for projects. The FPGA, of course, is under the heatsink there. Overall, a very advanced development board, but may not have the basic features for someone starting out, although we'll be using it for our simple arcade game core development throughout this series. So the project. The idea is to build together a simple arcade core on the MiSTer, from start to finish in Verilog HDL, meanwhile exploring all the tools we need to do it and exactly how we need to do it. The game I've chosen is Tank Battalion by Namco. It's a simple game from 1980 where you operate a tank and you need to defend your base from other attacking tanks. It can get tricky pretty quickly, but the main beauty is how simple the hardware design is. It took me a long time to find a very specific type of hardware that I could implement starting out, and I think that this game is ideal for the job. I'll get into more of the detailed review of the schematics in the next episode, but for now we can say it's a 6502 based design with tile hardware and very limited sprites. We have some footage of the game here from MAME, which is a great resource for playing games obviously, but also when we want to build a core, we can use the MAME version to check how it loads up, what RAM-ROM checks it might do, and things like that. The game has an attract mode, showing the main gameplay, and then pressing the coin insert button flips it back to the menu, and you can start in 1 or 2 player mode. The board has hardware dip switch settings, allowing you to set how many lives you get per coin, and bonus levels, etc. The main difference between the levels is really only the amount of walls and where they're placed. It's a unique mechanic in that you can change how the game plays out by shooting away walls in certain places. Graphics are very simple, but for 1980 it's a very playable game. The level completes when either the enemy has shot your base, or you've shot all the blue enemies. There's a counter of the enemies left in the bottom right of the screen. In researching for this video, I also found out there's a modern port for the good old Specky, and so that was a nice bonus. Go get yourself a copy from Indie Retro News. What's also good is that since I couldn't pick up this board to use for testing due to its age and rareness, I had the idea to build it up on a breadboard instead. By building it on a breadboard, we can take time to understand the logic chips we need to use, what each one does, and the basic building blocks we typically see in arcade hardware designs, at least in the early days. I can't guarantee that the breadboard design will work, but we'll certainly learn something doing it along the way. When we get into breadboard building, we'll be using other complementary tools, such as the logic probe to see if it's working. We'll also get to look at what the circuit is doing with a 16-channel logic analyzer that I'm showing here and comparing with the simulation in Verilog. If you're looking for info on old arcade games and hardware, I'd recommend starting off looking at the site system16.com. The site catalogues games based on manufacturer, telling you which games ran on which hardware boards, either certain generations or unique hardware. Here we can go to Namco for our game, and we have all the hardware they put out. You can then look at the releases chronologically, and you'll see 1980 we had Tank Battalion on a unique Namco architecture. There we have a description showing it was based on a 6502 CPU running at 1 MHz. Definitely a great site. Arcade Restoration, a website that allows you to check all arcade ROM versions out there. If we check for our game here, you can see there was an official Namco version and a bootleg. When we select the Namco version, we have a nice description of the CPU, the display type and resolution, and some info on the controls. This can be useful to know if your game was a 4-way or 8-way stick, which can be critical sometimes. Try playing Pac-Man properly with an 8-way stick. We have a description of the dip switch settings that I was talking about earlier, and if you're trying to implement a game, it's a great way to tell if you're on the right track with deciphering the schematics. We've got a list of the memory map detailing what each memory location links to, be it RAM, ROM, video RAM, or even input or output peripherals. Again, this info is essential when comparing to what a schematic is doing. Someone has already done the hard work, so let's use it. Arcade Italia is a site similar, but has some additional useful stuff like artwork, how the cabinet looked, and other info. Here you can see what the bezel would have looked like for the game. Pretty nice. Here is a German flyer for the game, showing a snazzy cocktail cab version of the game. And here is a nice view of the game PCB. As you can see, really not many chips on this one, and that's why we're going to be using it as the first game we will look at. Interesting to see here is a link to the MAME-C file, which is describing the game for MAME to use. This file can be a great resource to learn about a game, as it often has detailed descriptions of what the game is doing, translated from the schematics. MAME is very much doing a similar job to FPGAs in terms of mimicking how the hardware operates, but of course on hardware level, the parallel operation of FPGAs gets closer than the sequential nature of software emulators. For FPGA resources, I've compiled a few books that I think are really good for learning digital logic design and arcade architecture. The first one that does all of those things is Designing Video Game Hardware in Verilog by Stephen Hugg. This book really is amazing as an introduction to the subject of digital design and Verilog programming for those of us that really want to use it as an application to video game reproduction. The book goes from the ground up, from binary numbers and hex, discussion of TTL logic chips, and then launches into more difficult subjects of sequential circuits, including flip-flops and clock circuits. The book builds on projects chapter by chapter into finally showing a complete 16-bit home console architecture. My only criticism of the book is that I think, for the beginner, it cuts too many corners of the learning curve. You need those corners, and if you don't already know the subject, you'll end up not understanding what you're doing. For me, I had to build up my knowledge with other resources and keep coming back to Stephen's book to get more understanding. I think he just really knows his stuff and maybe takes for granted that everyone else does too. That being said, I'm very grateful that this book exists. Maybe another version could be done that could be expanded in scope and explanation. The companion website to Stephen Hugg's book is the 8-Bit Workshop. It has all his example code in Verilog there to play with. The website itself has many kinds of hardware covered, which goes along with his other books, such as developing games for the Atari 2600. But you can also look at code for other games consoles, computers, and arcade systems. It really is a treasure trove for developing for early systems. For Verilog, it has routines for displaying on the screen, and modules for tile maps and sprite hardware, and it follows the book's examples. As I said previously, there are some quirks to the way he does some of his coding, which may not help long term to understand how to develop for specific FPGA chips, such as how you might simulate block memory in an Altera system. But overall, you're learning a lot from this website and I'd really recommend it. No installation necessary, it's all on the website. On to general books about digital design, and I'd say the best book I've personally found is called Digital Design and Computer Architecture by Harris & Harris. It's the clearest book I've found that goes from absolute zero knowledge and describes the whole subject of digital design. The book covers number systems, combinational logic, sequential logic, and then introduces the hardware description languages for both Verilog and VHDL. The good thing about this book is that both language examples are shown equally, right next to each other when showing how to create a particular kind of design in digital logic. The presentation is second to none, and so I really love this book. One thing to note is that there are various versions of the book. The first edition is older Verilog, the second edition uses System Verilog, an update to the original, and then subsequent versions of the book have been written around different machine code architectures such as MIPS, ARM or RISC processors. You can pick the one you think is more useful to you. I got hold of a second-hand version of this book pretty cheaply. Another great book is Introduction to Logic Circuits and Logic Design with Verilog by Lameras. Like the previous book, this one also introduces all of the subjects from number systems, combinational logic, to sequential logic and finite state machines. This book sets itself apart in how well it describes the use of Verilog and the proper syntax to get all of your designs written. It's a perfect reference to have on your desk if putting together some Verilog code. There is a version of the book that deals exclusively with Verilog code without any digital design background, if that would be more useful to you. One thing to note is you can probably find electronic versions of these texts online if you look hard enough. Nandland, as described earlier, is the accompanying website to the Go board, designed by Russell Merrick. If you're starting out with zero knowledge of FPGAs, I would really recommend this website, and possibly the Go board too, although you can still use the website with your own hardware. The website introduces many of the concepts to do with FPGAs. It covers the difference between the two most common FPGA languages, Verilog and VHDL, and shows where each is most prevalent. Every example on the site can be looked at in either language, and it's a great resource for sure. HDL Bits is a website that you can use to test your Verilog code writing skills. The site has a large number of problems for you to solve by putting in the correct solution to the problem at hand. It only offers limited description of how to solve these problems, so it's not going to be your one-stop shop for learning Verilog, but it certainly helps you build confidence that the code you're creating is correct. It's also pretty fun to complete the challenges it gives you. There is not only one right answer. EDA Playground is an online Verilog compiler that can be used to run code simulation. The beauty of the website is that it's all web-based and therefore you don't need to install anything. It's perfect for the smaller snippets of code you want to get working, maybe away from your main computer. You can save your own library of routines or playgrounds that you can then select from and then run, even with graphical outputs of the waveforms. I've typically used it to get individual Verilog reproductions of various 74 series logic chips working and checking them prior to putting them into a larger design. We'll be taking a look at that in future videos. Of course, if we're going to do any development for the MiSTer platform, we're going to need the software on our computer to be able to do it. For us, that means installing the Quartus 2 or Prime software. We need to go to the address shown and also linked in the description and choose the light version of the software and version 17. Developing for the MiSTer requires version 17.0, so don't go for the latest version. You can select the individual items if you want to install them separately. If you do that, you'll need the Quartus Prime software, the model sim, and also the Cyclone 5 device support files. Get that downloaded and installed and you'll be on your way. Since we also want to do a bit of hardware tinkering on this project, using an actual CPU, some logic chips, crystal oscillators and breadboards, you'll want to find those components from somewhere. Or, if you're trying to fix an old arcade board, you'll need that stuff too. One great resource for some older ICs is Jameco. They sell high quality breadboards, which you will want if you are to have a successful project, as cutting price here is not a good idea. You can get your CPUs from here, be it the older versions or even the newer types if available, such as the Western Digital 65C02, an updated CMOS version of the older MOS 6502 chip. Many of the most common chips are available from Jameco, so it's my first port of call for a project. For some ICs specific to arcade boards, you may need to go to a specialist website. One example is Twisty Wrist Arcade. They specialize in those really obsolete things like specific kinds of RAM or ROM memory chips or PROM chips that you just can't get from anywhere else these days. For this project, I had to buy a color PROM chip from here and get it sent away to be programmed. We'll get into that detail a bit later in the project. There are also other similar sites out there. Grant Searle's website has become very famous for those people wanting to start out creating single board computers based on Z80, 6502 or 6809 CPUs. He does a really good job providing simple schematics for adding RAM, ROM and some glue logic to produce workable computers with very minimal parts. Also, his designs are based on creating old computers with modern parts, so something that a lot of people are looking to do. Check out his website since he has lots of useful information. One thing he has is the IC stickers that you can put on your chips to help identify what leg is what when building up breadboard designs. That alone is worth the visit. The Constructor Virtual de Circuitos Digitales, excuse my Spanish, is an amazing tool that allows you to build breadboard circuits without having to ever touch anything real. You can put a virtual breadboard together with many of the chips that it has in its library and see how they operate, by linking them to timers or LED banks. I found it very useful if you want to understand a particular logic chip, comparing it to the chip's datasheet and logic table before implementing it in Verilog code. The blog shown here has the tools available for download, in addition to a handy TTL Logic Series datasheet compilation book. Go grab it for yourself. Finally, a pretty oldie but goodie book called Video Game Logic, written by a guy that would fix up the early arcade boards of the late 70s. The book does an excellent job at describing the elements in these original arcade games of the era just at or before the introduction of CPUs to board architecture. He covers the basics of digital logic and what chip does what, but also goes into the really important items of how a TV display works and what display timing circuitry is needed in order to get a picture on the screen. We'll be looking at and creating circuits very similar to these, so it's a great grounding in the basic building blocks that you'll find in these early arcade boards. This book should be available from the website provided, or from others if you search for the book online. Before we go on to see more about the project, I'd like to just take a moment to point out that while I am an engineer, I'm in no way an electrical engineer with a formal background in hardware design. Everything I'm speaking about in these videos has been self-taught through books and the web, and while I think I have something to offer the beginner trying to write their first bit of FPGA code, I'm probably making a bunch of errors to those that have been formally educated. Go easy on me, any errors are not intentional. If there are glaring errors, please let me know in the comments, but also understand that I'm trying my best in a pretty complex endeavour. Okay, so let's get going on the very first basic MiSTer project. This is really just a D10 Nano project using the MiSTer I/O board LEDs as output. It's not the MiSTer because we're not using the functionality of the MiSTer libraries. We really only do that right at the end of our Tank Battalion project to get the controls working. So we're going to write our source code to blink an LED on the board. I'm using a program called Programmer's Notepad. It's just personal preference since it's simple, does syntax highlighting for Verilog if you have Verilog chosen. It's also really good for highlighting common variables that can be very useful. I've saved a blank file called blink.v. I'm going to create a top module called blink. We'll have an input and an output and close with brackets. Then close the module. The input is going to be the clock on the D10 Nano called FPGA _clock 1 _50. It's one of the 3 50 MHz clocks on the Nano. We can put a comment in the code like this. The output is the wire LED power on the I/O board. We'll create a 32-bit register called count. Then, using an initial begin block, we'll set the 32-bit counter to 0. I'm doing this here in hexadecimal format. I've used a non-blocking statement to do this. If you want to follow along with the previous Lamera's book I mentioned, this is covered in section 8.1.2. For this particular instruction, I don't think it really matters whether it's blocking or non-blocking. We'll add an always block to trigger an event on the positive rising edge of the 50 MHz clock, like this. We'll make the counter increase by 1 every positive edge of the clock. Let's assign the LED wire to be on if counter bit 24 of 32 is 1. We'll save that code. Okay, let's start quarters prime. We want to open a new project wizard. Select the folder Blink1 that was created previously. Call the project Blink1 and the top level module was called Blink. It needs to be the same as the module we just wrote. Add all will find the Verilog files in the folder automatically. Next, we have to choose the device. It's a Cyclone 5 SE base. We need to choose the BU2317DK. Then it's optional to choose the simulation software ModelSim Altera. Press Finish to set up the project. Click on Blink and that is our code. It also has the syntax highlighting, which is useful. We said earlier that the LED wire to be on if counter bit 24 32 is on. That means the counter is counting to around 16 million before the bit is on or not. If the clock is 50 MHz, it's still a bit fast at 3 times a second. We'll fix that in the Quarters 2 software by adding a PLL or phase locked loop. It's an automatic way to create new clocks from higher frequencies, which we will almost always need to do since the reference clock is 50 MHz. If we go over to the right here, we have the IP catalog. We look for the basic functions, clocks, PLLs and resets, and then PLL. We want the Altera PLL. We need to give it a name. We'll call it clock_PLL. That starts the Mega Wizard, which is a really grand name. In the Mega Wizard, we're going to disable the locked output port. We don't need that. We're going to ensure we only have one output clock, since that's all we need. We'll change the input reference clock to 50 MHz, since that's what we have with the D10 Nano. And then, let's change the desired frequency of the PLL to 5 MHz, making our clock 10 times slower. We don't want to touch any of the other items. You can do lots of complex stuff here, I'm sure, which we don't need today. Press finish, and that will start the process of creating a PLL. It takes a while. When it's done, hit exit. It'll then ask us if we want to add the quip file to the project, which we do want to. You can do it automatically if you want. If we then go up to Files here, you can see all the files in our project. By opening the quip file, it shows we have the clock_PLL in there. Double click that to open it. In this file we have the module linking to the PLL here, and above the declaration of the module, that's what we want to instantiate in our code. I tend to copy the module and then paste it back into the module I'm using it in. Once it's copied in, I then delete the part so I'm left with the required inputs and outputs. Here I'm instantiating the model of the PLL that is defined in the other file. I'm using explicit port mapping with a dot or period rather than positional port mapping as a preference. If you want to check this out in the book, it's section 5.6.1. The reference clock input we will set to be FPGA clock 150. We're going to leave the reset input blank, and the output we're going to need a new wire to feed into our current design. Let's create a wire just called clock. And then put that as the output to the PLL in outClock. Now at the moment our always block is triggered on the positive edge of the fast 50 MHz clock. we want to change that to only be on the slower 5 MHz clock output from the PLL, so we'll change that to clock instead. And save that. Let's compile our design by pressing the blue triangle play button. You can see here with the red warnings that we have an error in our code. You can see here that the compiler is expecting a different syntax, so let's see what we did wrong. Yep, the end module syntax is wrong. We should have seen that with the highlighting anyway. Let's fix that and compile it again. Notice the error we get isn't exactly what was wrong, so you have to become good at understanding what it's trying to tell you. I want to make simple errors in these videos to show you the typical things that can happen. I've sped up the compilation process in the video, so don't think I have some amazing supercomputer. Okay, done. We have our code compiled, but at the moment it has no way for the FPGA to talk to the outside world, because we haven't assigned the pins to do that. The clock for the FPGA is on the board, not on the chip, so it needs a pin assigned, and so does the LED. That is actually on an I/O pin. Let's go to Assignments, Pin Planner to do that. Here you can see our 2 pins waiting from our design. If we go to the location, we can pull the drop down box and select pin V11 for the clock. It also needs to be set to 3.3 volts LVTTL. And the power LED is on pin AG28. That can stay at 2.5 volts default. So that's now done. Let's compile again. There, done. So now we need to upload to the MiSTer or the D10 Nano with an I/O board. We need to plug in the mini USB cable to the location just below the VGA port and the other end into the PC, and also attach the power. Then we turn it on. Now we need to upload our design to the FPGA. Go to Tools, Programmer. The D10 on MiSTer needs to have 2 chips showing up in the bottom box, the System on Chip box and the FPGA. So let's press Auto Detect and then say yes to the chip highlighted. Now we have the System on Chip there as well. We don't have the correct version of the bottom chip. So let's delete it and add our output file over here. Go to Output Files, choose the blink.sof. Now it's just right for both the SOC file and our file to load the FPGA. Now if we press Start, it will upload the FPGA and say 100% success in the green on the top right. And there we have it, a slowly flashing yellow power LED. We've done our first FPGA programming on the MiSTer. Well, thanks for joining me. Next time, we're going to start to look in more detail at the tank battalion hardware and start to set up the clock timing circuitry on the breadboard and in Verilog. If you like the content, please like the video below and also subscribe to the channel to be notified when I get a new episode out. See you soon!